Here I am briefly presenting the paper Good, Cheap and Fast Overfitted Image Compression with Wasserstein Distortion. It was published as a poster at CVPR 2025 and received a highlight. This work is based on C3, an overfitted image compression method. In overfitted compression, the encoding of an image is done by fitting a decoder model to one specific image. The objective of the encoding optimization is a weighted sum of rate, the size of the compressed bit sequence, and distortion, measuring the difference between the original image and the reconstruction. The decoding of the image is given simply by running the model. Compared to many neural network applications, decoding can be very fast since the model doesn't need to be very large to achieve good performance. To measure the difference between the original and reconstructed images, we can choose different distortion metrics. A simple choice is MSE, the mean squared error between pixel values. However, this choice does not align well with human notions of differences between images. It has been observed that neural network features from object recognition networks such as VGG, correlate with recordings of neurons in the visual cortex. LPIPS, a recently proposed image distance metric, exploits this by measuring distances of object recognition features rather than of pixels directly. It has been shown to perform much better than MSE on predicting human responses in rating tasks, such as the triplet task shown here, where a rater must choose which of two distorted images looks more like the original in the center. However, few image metrics take into account the difference between foveal and peripheral vision. In contrast to the center of gaze, where our vision is most accurate, we tend to perceive texture statistics rather than precise detail in the visual periphery. Wasserstein distortion models this. It does so by aggregating empirical distributions of features in a local pooling region, which can have a spatially varying size. It compares the statistics in each pooling region from one image to the other, rather than the features directly. In the center of gaze, the pooling regions are so small that the metric converges to comparing features directly. In this way, Wasserstein distortion generalizes LPIPS. Concretely, for VGG features, this means we extract specific feature maps for each image. While LPIPS compares the features point-wise from one image to the other, Wasserstein distortion compares local statistics of pooling regions, whose sizes are generally different depending on the location. Here's a concrete example. The right-hand image was initialized randomly and optimized to a minimum Wasserstein distortion with respect to the left-hand side. Initially, it might be hard to see a difference. However, take a look at the top right. We used a saliency map to inform the size of the local pooling regions. In high saliency regions, a small pooling region was chosen as these regions may be scrutinized by a human observer and would hence be in the center of gaze. In low saliency regions, a large pooling region was chosen to account for peripheral vision. This makes the metric permissive to texture resampling. In this work, we make three technical contributions. First, we replace the distortion loss by Wasserstein distortion. Second, we provide pseudo-random noise to the encoder and decoder, which helps in reproducing texture. And three, we propose an approximate but fast implementation of Wasserstein distortion. The fast implementation is based on the idea that local statistics with pooling region sizes of powers of 2 can be computed with the help of multi-scale filtering. We can obtain local estimates of the first and second raw moments by building a Gaussian pyramid on both the feature value and the square of the feature value. The local variance can be computed by combining the first two raw moments. The local Wasserstein distortion is then simply a function of the local mean and the local standard deviation. As long as we round or interpolate the pooling region size, Wasserstein distortion can be computed quite efficiently this way. Here's an example of a reconstructed image at equivalent bit rates. On the left side, C3 was optimized for mean squared error between pixels. On the right side, it was optimized for Wasserstein distortion. The latter is more permissive with regards to resampling texture, which can help substantially to use the bitrate more efficiently. Here we illustrate that choosing the pooling region size based on saliency can help identify parts of the image that may be visually scrutinized, and thus have a higher chance of ending up in the center of gaze. One such part is the text on the lens. By choosing small pooling regions there, Wasserstein distortion encourages precise reconstruction of the text, while still enabling a more efficient reproduction of texture on the shirt and the skin. We conducted a human rater study to determine how well the new model performs in terms of bitrate versus visual quality. We find that to achieve the same quality with an MSE optimized model, twice the bitrate must be spent on average. The visual quality achieved by our model is comparable to that of a much larger model optimized with an adversarial loss. However, our model is 2 orders of magnitude faster in decoding, comparable to commercial codecs such as VVC. We observed also that Wasserstein distortion is extremely good at predicting human ratings on all compression methods we compared. In future work, we would like to find additional applications of Wasserstein distortion and also expand it to video. Thank you for your attention.